We have a little over 5 minutes for questions related to any of this morning's talks. So do people either in the room or online have any things they wanted to go back to, or continuing follow-up on Josh's talk? I'll give it, oh.
It's not a question, it's just a shameless plug following off of Troxel's talk. So in the Supernova Pit session, I think it's tomorrow, I'll be showing the simulations that Troxel and Arun did based on what he showed here for the Prism. So if you're interested in how we're doing that for the slitless modes, come see me tomorrow.
Awesome, thanks. Yeah.
Hi, Michael Woodvasey. What's the in-flight commissioning and calibration plan that picks up and checks and relates to the TVAC testing?
So sorry, turn this back on. So the question is, what is the in-flight calibration plan that sort of cross-checks a lot of this? Yeah, so that is a very lengthy document that has a draft that's currently been written. And it's now, in further development based on what we've learned in these run-for-the-record TVAC tests. And so, the kind of questions that have been asked after this presentation are all the right ones to ask. We learned what we could with our telescope simulator and the environment in the TVAC chamber. We've characterized these subsystems of this instrument as best we can, but now we have to think about what does that mean for the flight configuration and what does it mean for actually observing astronomical sources. And so that calibration plan is in work. Aspects of it are discussed in our calibration working group. And so if you're interested in that, I would encourage you to tune in. There's been a lot of discussion recently on touchstone fields in the calibration working group and what kinds of fields we will observe and revisit throughout the mission for calibration purposes. And so, yeah, there is a plan. It's been written in draft form, and it's currently in work and being revised based on what we've learned from all of this ground testing. And we're looking forward to continued input from everyone in the community as we share these results more and talk more about that calibration plan to make sure that we're doing all the right measurements so we fully understand the instrument and it's ready for science.
So these are all point sources. Is there any support for spatial scanning? I can't remember where that left off.
Might defer to Jeff Kruk or Julie to answer the question about support for spatial scan observations.
So at the moment, it's not actually formally supported. I've been working with the attitude control system team since they came into existence, telling them that we will at some point probably have to do that. The flight software does support doing spatial scans. At least unguided spatial scans, so it would be just on the gyros. But at the moment, the hooks and the planning system aren't there to implement it. And so I won't say we aren't going to do it, but right now, the particular motivation, for example, if there are specific calibrations that really require that, then we would put the plan into action, but at the moment it's not there today.
I think there was one more question up there, was there? Yeah, right there.
I was just curious, you said that the persistence goes away pretty quickly. What does that exactly mean?
Okay, so I did not put that plot in this talk, and that was my mistake. Let me see if I can remember exactly how this works. So there's a long story behind the persistence characterization of these detectors because it's a critical aspect of building a sensitive survey capability like the Wide Field instrument in Roman. And so we did very detailed persistence testing on individual detectors when they were being selected to be placed in the flight focal plane to characterize their persistence performance. And what was done there is we did a low flux and a high flux persistence measurement where we flooded the detectors with flat field light at multiple wavelengths, and we monitored the persistence decay over time. In those tests, we never got up to levels that were much higher than maybe 5 times the full well of a pixel, so maybe 500,000 electrons or something. And that persistence decayed away. Most of it decayed away within about 10 minutes. And there's some tail that lingers longer than that, maybe out to 30 minutes or even an hour, but it's very low. In this test, in this particular PSF, the core pixel there is receiving about 25 billion electrons, as opposed to the something like 500,000 that we did in lab testing. And if you take these subsequent persistence measurements that we kept doing over time and we monitor the decay in the core of this PSF, we actually find that the data is pretty discrete. We don't have like a very continuous trend. But if you take what we have and you compare it to what we saw in the lab, it's almost exactly the same. So the persistence decays away quite quickly, even though we've really flooded these pixels with high flux. We're still working on that. I wouldn't take that out as sort of a ground truth right now. But it appears in early analyses of these data that even for the very, very bright point sources, that the persistence decay is comparable to what we saw in lab testing to characterize the detectors up front.
All right, so let's thank Josh and all the morning speakers again.